So now we've looked at how the basics of computers work. We looked at the four-stage model. We talked about input and output. We've talked about bits and bytes. We've talked about CPUs and logic gates. Now we come to the software. So how do we put these instructions together for a computer to understand? So now we're going to talk about computer instructions and code. And we're going to look at how a computer reads instructions and knows what to do. Or better still, how we communicate and let the computer know what to do. Now, we know that we use zeros and ones. Our computer speaks in machine code, machine language. A machine language is basically ones and zeros. And it can tell the switches, determine the switches, because that's how it understands. And each chip, as we've mentioned before, comes with a set of basic instructions, either reduced instruction set of computers or complex instruction set of computers. And each byte, or maybe 2 bytes together, can represent a command and data. So a command might say, okay, one particular instruction comes in and it says, go and fetch the contents of the next memory address. And then the next byte might be the next memory address. So all code is understood by the computer as a series of zeros and ones. And there's the problem, because the computer understands zeros and ones or machine codes, but humans find it quite difficult to work with zeros and ones. Can you imagine having a program with thousands upon thousands of zeros and ones together, and then having to go and look at the program and having to decide what's going to move and where? Or worse still, somebody wants to change. So how do you go and find the particular sets of zeros and ones that you're going to change? Very, very difficult. But you know, assembly language is very close to that, but it's still the same thing. Now, we used to write code using pretty much hexadecimal, and assembly language instructions usually are written with hexadecimal. So what's hexadecimal? Well, we've talked about binary, we've talked about putting things into bytes, and we looked at the binary numbering system. Hexadecimal is a counting-based system on 16. So we count from 0 to 16, not from 0, 1, 2s as we do in binary, but from 16. And we have 16 different characters, 0 to 9 and A to F, that represent our characters. So now actually that can represent 4 bytes of information rather than just doing it with zeros and ones and doing 1 byte at a time. And if you have a look at the table here, we've got some examples there. Each character represents 4 bits. So if you have a look now, instead of having to worry about using the binary zeros and ones, we've grouped them together and made them easier to understand, or a little bit easier to understand. If you have a look at our table, so you've got a hexadecimal value of 6, the binary value of that will be 110, and the decimal value will be 6. And as we go up 6, 7, 8, 9, then we get to A, which represents hexadecimal, and then 1011 for binary, 10 for decimal. So you can see the systems match up, but it's an easier way of writing. So hexadecimal, you'll see a lot if you play around and you have a look at some of the code that's decompiled, you'll see a lot of it written actually in hexadecimal. So it allows us to read more and put more into a computer a lot quicker. However, it is still very difficult to write code. So we use something like machine code or assembly language. And here's an example that you can see on your screens now, where you can actually see some very basic instructions. And assembly language and machine code is actually very, very basic type. So you might have things like move, and, pop F, push F. You might see things, you have loop. So these are very, very basic instructions. And next to it, you'll see particular data and our interpretation. So basically we convert from ASCII to binary code decimal. Then the next line says get the next digit of counter in the arithmetic and logic unit. Then we recall the carry flag. Then we go through, but this is machine code and we don't have to understand machine code or assembly language anymore. Okay, very basic commands, very simple, but you might recognize some of the things as we go later on to look at programming. For example, things like loop, return. These are things that we see before. And here's another example which gives you ideas. So we've got our little loop Then we've got an else and an end if and an end loop, and these are the beginnings of the languages that we're going to put together. But these all form very, very basic components, very basic commands that the computer will understand, and you can begin to see the patterns. However, writing code with this is very, very difficult. And if you're going to write really, really big systems, you'll see that it's really difficult to manage those systems and make sure that your code is written properly. Very hard to debug, very hard to maintain. So the big problem there is working with all this stuff could be a nightmare. And programming wasn't a fun thing to do in the early days, especially when we were using punch cards to do it. But you know, we don't want to program in ones and zeros. We don't want to write our code in ones and zeros. We haven't got much control. It's very inflexible, very difficult to modify, and very difficult to maintain. So we have the advent of computer languages. And on our diagram here, you can see where our languages started off. In the blue box, you'll see the very early basic languages that we had. Things like Fortran, Algol and COBOL were pretty much amongst the first languages that came along. COBOL, very much a business language, and there are still many, many systems out there that are running that were written in COBOL. So there's still plenty of room if you want to be a COBOL programmer. Very limited, but lots of work out there. Somebody's got to look after them. And then we came along with things like BASIC and Lisp, which was more of an educational type program, Forth, BCPL, and quite a lot of other languages that started coming along. But then we moved up, and then we had things like Perl, Pascal, and C, which gradually became more modern. Pascal is really the basis of a lot of the languages that we have now. Java, Ada, C, C++, these were very much written along the lines of the Pascal programming language, which is an earlier university type language, teaching type of language that took on evidence. And in fact, one of the first object-oriented languages, which was Ada, was actually based on Pascal. And then we move up, and now we have the languages a lot of people are pretty much using these days. Things like Java, C++, C#, the Microsoft version. Ada we don't use as much these days. JavaScript, which you'll see used in a lot of browsers, even though it's supposed to be more of a scripting language than an actual system type of language. And then in the earlier days we had Smalltalk, which was again, like Ada, one of the earliest object-oriented languages. So we gradually move up. The first generation sequential languages starting from 1950, we had the basic programming languages. Then we moved up to the pre-object-oriented languages such as Perl, Pascal and C, and then we had the object-oriented languages and the birth of the internet, which of course they were used over. And that's why Java became so popular really, because of the internet and because of being able to write things called applets, which would run in a browser. And then we've got other languages such as Python, which have come across, Python, Ruby, and these are newer languages, but a little bit smaller. Python being a really, really useful language, used in a lot of data science and very good language to start learning with. So our languages have moved up, and basically we've moved further and further away from the assembly language. Further and further from the way the computer understands it, and we end up looking at languages that we understand, English language, or in a language that we understand, rather than using a language the computer understands. And this is what we call abstraction, as we abstract out the details that we want and that we can understand, and to make programming something that's an efficient and effective way of writing code. The higher up we go, the further away we get from the bits and bytes, and the closer we get to understanding and controlling the instructions. You could say that the applications that we write sit on top of these languages and are a further abstraction from that machine code. So something like the text-by-word processor, a spreadsheet, a database, these are really a graphics package, an audio package. So these are just moving up the scale and becoming more and more specific, so that people are going to use it and further away from the zeros and ones. And why? Well, because we find it very difficult to understand zeros and ones, but we know how to use the tools that we develop using these languages that have been created. So, how do they work? Well, basically, the language is written to understand more like English. And we've got an example, a couple of examples here that we can run through. But there's two ways that our languages work. We can either have compilation or interpretation. So what's the difference between the two? Well, if we look at the program at the top, which is a C program that basically says hello world. Okay. Now once we've created that and we've written that in our text file, we then have to compile it, i.e. the compiler has to take the words that we've written or the file that we've written and convert that file into the binary code that the computer will understand. And that's called compilation, because at the end of it, we end up with an executable file, which is basically zeros and ones. And it's a file that the computer will understand. So we take the English, the written language, the programming language you've used, we write it in a text file of some sort, we then push it through a compiler. We might have to do some sort of linking with other bits and pieces as well, but if we just compile this piece of code, that will give us the zeros and ones, and then we run those zeros and ones because the computer understands what to do. The drawbacks of this type of thing is once we've compiled it, it will work, and it will work on that particular machine or that particular platform with the specifics of that particular processor, because it will range the zeros and ones in a way that that processor will understand. So we can't take that compiled code and take it to another platform and try and run it on there. We would have to take that code and compile that original code that we wrote and then recompile it on a platform, on a different platform, in order to create the executable code that will run on that platform. So that's how C++ works. Now let's have a look at something like Python. Python is an interpreted language. So what does that mean? Well, that means instead of compiling it and creating lots of zeros and ones and then running those zeros and ones, the interpreter does exactly what it says. It interprets that code line by line. So the actual Python interpreter sits on the machine, and when we run our code, it will take each line, one line at a time, and compile it and run the instructions. So we don't get a compiled file at the end of it, because it's running the instructions as it goes along and compiling the instructions as it goes along. So as you can see here, we've got just a print hello world, and doesn't it look like an easier program to run than the one above? When we run it, we do a Python hello.py. Automatically, if you convert, the interpreter kicks in and starts converting and translating that code. And then we get the program being run. So two different ways of doing things. Now, when you look at Java, another language works in does both. And why does it do that? Well, because we want to make it so it can run on any platform. So what happens with Java is we have something called the Java Virtual Machine, and the Java Virtual Machine, or the JVM, when you compile your piece of code, and that creates something called bytecodes, which is pretty much like the exe file that we saw earlier on. And then with that bytecode, you can then go ahead and run that bytecode on any platform that has the virtual machine installed. And each platform will have its own version of the virtual machine that knows how to interpret bytecode and to make it run automatically for that particular platform. So Java really uses the two together to actually make things work and make their code interoperable wherever it goes. So that's languages. Now we're going to investigate some of those languages. There is, of course, how to write Python, how to write Java, and you can go ahead and find on the internet all different ways that will teach you and show you how to run these particular pieces of code. So the very next thing is to get stuck in and start programming.